everyone, let's dive right into this explainer and demystify the seriously fascinating world of mathematical sequences and progressions together. Whether you're gearing up for a big exam or you just kind of want to understand the hidden mathematical codes that govern our universe, you are absolutely in the right place. Here is our game plan for today. We'll kick things off with real-world patterns and sequences. Then we'll break down explicit and recursive rules. After that, we'll tackle arithmetic progressions, or APs, followed by geometric progressions, or GPs. Finally, we'll wrap up with a master formula sheet and some practice. Let's get to it! Section 1. Real-world patterns and sequences. Seeing math everywhere. Let's start with how math just naturally pops up in the physical world around us. Patterns help us make sense of the world, and more importantly, they let us predict what's coming next. Notice how these physical objects create perfect mathematical sequences. On the left, we've got tennis balls forming triangular numbers, 1, 3, 6, 10, 15. With every single step, you're adding a new row to the base. And on the right, those marbles perfectly illustrate square numbers, 1, 4, 9, 16. It's not just abstract stuff on a textbook page, It's geometry you can actually touch. So, the crucial point here is that a sequence is simply a predictable pattern translated into an ordered list of numbers. Each number in that list is what we call a term, and its placement is its position. Take our square numbers, for example. The first term is 1, the second term is 4, and the fifth term is 25. Make sense? Moving right along to Section 2, explicit and recursive rules, cracking the code. Now that we can spot the patterns, let's learn how to actually write the rules that predict them. In math, we use a specific notation like t sub n to represent the term in the nth position. And there are two main ways we can define a sequence. Think of an explicit formula like dropping a precise GPS pin. You plug in the position number n, and it takes you straight to the value of that term, no matter how ridiculously far down the list it is. A recursive formula, on the other hand, is basically giving you step-by-step directions from where you currently are, meaning you absolutely have to know the previous term just to figure out the next one. Let's see this in action and watch how it builds using an explicit rule. Here, our rule is t sub n equals 2n minus 1. By simply swapping out that position number n with 1, 2, and 3, we instantly generate the terms 1, 3, and 5. Notice how we didn't even need to know the second term to find the third term? That right there is the magic of an explicit rule. All right, Section 3, arithmetic progressions, or APs, the power of addition. Okay, let's dive into our first specific type of sequence, known as an arithmetic progression, or AP. This is a pattern built entirely on consistent addition or subtraction. And hey, here is your first major exam formula. An AP is defined by a starting term, which we call A, and a constant common difference, called D, that gets added every single time. But as your math guide, I really don't want you to just memorize this formula. I want you to truly understand it. Why do we use n minus 1? Well, since our first term A is already our starting line, we only need to start adding that common difference D from the second term. So if you want the 10th term, you only add the difference 9 times. Pretty intuitive, right? Watch carefully as we break this down step by step to build our very own explicit formula for this sequence 1, 5, 9, 13. Step 1, our starting term A is 1. Step 2, we're clearly adding 4 every time, so D is 4. Step 3, we just plug these into our master formula. Distribute that 4 into the parentheses, combine your like terms, and boom, we get the beautiful, simplified, explicit rule t sub n equals 4n minus 3. Now, let's flip the script. What if the exam asks you to work backwards? Here is a golden exam tip for you. Whenever you are given the final value of a term, set up an algebraic equation. I actually want you to pause the explainer right here, grab some paper, and try to solve this yourself before I reveal the answer. Go on, give it a shot. All right, how did you do? Let's look at the step-by-step breakdown. If you set 607 equal to 5n minus 3, added 3 to both sides to get 610, and then divided by 5, you found that n equals 122. If you got 122, fantastic job applying your algebra skills to pinpoint the exact position of that term. Section 4. Geometric progressions, or GPs, multiplying to infinity. Let's do a quick mental reset before we shift gears from adding to multiplying. Welcome to the wild world of geometric progressions, where numbers scale incredibly fast. Here's the core difference between the two main progressions we're studying. APs grow steadily by addition, step by step, GPs, however, can literally explode in size through continuous multiplication. Instead of a common difference, we're now dealing with a common ratio, denoted by the letter R. And here is your second major formula. T sub n equals A multiplied by R to the power of n minus 1. Just like before, the absolutely crucial piece here is that n minus 1 exponent. It guarantees that our first term, A, isn't accidentally multiplied by the ratio right out of the gate on day 1. You only start multiplying by the ratio to get to the second term. Let's apply our brand new formula to this sequence, 5, 25, 125. We carefully identify our starting point A as 5. To get from 5 to 25, we multiply by 5. So our common ratio R is also 5. Plugging this into our formula for the 10th term, we get 5 multiplied by 5 to the power of 9. That's a massive number, so I'll let you calculate that one on your own. Let's try another pause and solve challenge, but this time we're working with exponents. Grab your calculator, identify your A and R for the sequence 2, 6, 18, set the whole thing equal to 4,374, and see if you can solve for the position n. Okay. Let's review the steps. Our A is 2, our R is 3. We set 4,374 equal to 2 times 3 to the power of n minus 1. The first and most crucial step is dividing both sides by 2 to isolate that exponent, which leaves us with 2,187 equals 3 to the power of n minus 1. By systematically testing powers of 3, we reveal that 3 to the 7th power is 2,187. Therefore, n minus 1 equals 7, which means 4,374 is exactly the 8th term in this progression. Now, GPs aren't just abstract math meant to torch you on exams. They perfectly model real-world physics. Think of a bouncing ball dropping from 80 meters and losing exactly 40% of its energy on every single impact. That means it bounces back to 60% of its previous height. This creates a geometric sequence where A is 80 and your common ratio R is 0.6. You could literally calculate exactly how high the 10th bounce will be just by using the GP formula. Finally, Section 5, Formula Sheet and Practice, your exam toolkit. All right, let's pull everything together into a toolkit you can rely on for test day. This is the culmination of everything we've broken down today. This master formula sheet is incredibly valuable, guys. I highly recommend taking a screenshot of it right now for your study notes. It houses the AP formula with its constant difference, the GP formula with its constant ratio, and even the explicit formula for those triangular numbers we saw way back at the beginning of the explainer. But having the formulas is only half the battle. You've got to watch out for these common mistakes. The absolutely biggest trap I see as a teacher is students forgetting the n-1 when they're stressed out. The second biggest trap, swapping addition for multiplication when under pressure, completely mixing up D and R. Take a breath, stay calm, and always identify if the sequence is adding or multiplying first. I'm going to leave you with this final real-world puzzle to test out your GP skills. If a culture starts with 30 bacteria cells and doubles every single hour, how fast does exponential growth really happen? Try writing the explicit formula for the nth hour. Think about it. If a single cell multiplying can take over its environment in just a few days, what other invisible sequences are silently multiplying all around us right now? Food for thought. Until next time, keep looking for the patterns.